Topic 5-4, exterior angles of polygon. This can be referenced with our Holt book, Chapter 6, Section 1, page 384 through 385. Alright, start off with the definition of an exterior angle. Angles formed by the sides of a polygon and the extension of an adjacent side. Lots of vocabulary terms. So look at the example that you have to fill in the blanks. This could be a side length. This is an exterior angle because it's on the outside. And color it in. And this line right here, we'll highlight it, is the extension. The extension that extends outside of the triangle. You can see that highlighted. Let me show it with an example. If you've got a triangle, and this is your side length, this would be the angle formed by the outside, and this extra line that I've put to the triangle is the extension. And we're going to draw some extensions on the next two polygons, so you're going to need a ruler. You might want to pause if you don't have one, go get one. Alright, so when we're going to put the extensions of each of these polygons, it's taking the line, lining up with it, and following that and extending it out. Slide it around and do each one in kind of a pattern. So that, notice how I'm continuing to go around this polygon that appears to be a square and drawing the extended lines in kind of like a spiderweb way. If you were going to mark the exterior angles of this polygon, they would be right here, adjacent to the side, the extension of the adjacent side, or the exterior angles of a polygon. This is a six-sided figure, so it's a hexagon. It looks to be a regular hexagon. Remember, equal angular and equilateral is regular. But again, notice how I'm going in a pattern all the way around, making this extension from the vertice following the vertice before it. So you should be able to create only 6 extensions on a 6 sides. Don't add extras, but if you'll do it in a pattern, you can show all of these. Mark them, exterior angles. We're going to come up with a formula to be able to denote exactly the measure without a protractor of these angles. So how does the number of exterior angles compare to the number of sides? Well, we just mentioned that it has to be the same, so they're going to be the same. Those would have the same number. We previously learned how to find the sum of the measures of interior angles by using the formula. Remember, it's the sum of the angles, and they're the inside. Interior angles was equal to taking the number of sides, subtracting 2, and multiplying all of that by 180. So that was our formula. Let's go to example 2. Find the sums of the interior angles of an undecan. If you'll remember, that was an 11-sided figure. 7 minus 2, let's just copy the formula again. Number of sides minus 2 times 180. So 11 minus 2 times 180. And that would be 180 times 9. So again, remembering that we're looking for not one angle, but the sum of the angles, would be 1620. That would be equal to 1620. Similarly, there is a formula to find the sum of the measures of the exterior angles of a polygon. For the exterior, and remember, you're still dealing with sums, not one angle itself. That's equal to, guess what? Always, always, always the same. No matter how big or how small your polygon is, you'll always find that adding up the sums of the exterior angles is going to give you 360. So the sum of the measures of any polygon in example 2, which could be the 11-sided polygon, I'm not going to draw one, but just know they're going to be 360. And remember that this is the sum. I'm going to write that big since I've got a big enough space for it. So we have learned that in a regular polygon, the polygons that have equilateral and equal angular, so the exact same for every side length and the exact same angle measurement for every angle on the inside, the interior form, and also on the outside too once it's equaled up. So if we do have a regular polygon, we can find the measure of one of its interior, meaning on the inside, by using the formula. So if you want each, this is where it's not the sum, but it's each interior angle. If you need each interior angle, then you're going to take that formula that we first found out that would give us the sum of all of them, which was 180 times the number of sides minus 2, and divide all of that by, since they're all supposed to be equal angular, the number of sides that we have. And dividing it by the number of sides we have is going to give you the measure of just one of those angles. So let's find the measure of one interior angle of the polygon described. Again, we'll keep using example 2. So if we drew an 11-sided figure, we know that we have the total sum using this formula gave us 1620. So you would take that 1620 and divide it by the 11 sides. And that's going to give you, let's see what they told us, 147, I might have to use a calculator, I'm trying to read them, 22 degrees. Hang on, let me make sure that's a decimal point. Let's go to our calculator. Clear this out. You've got 1620 divided by 11. Oh, they did just round it, and notice how it repeats. That's why to show a repeating decimal you would show a bar over it. So 147.27 degrees. So it's not a nice round number, but it is the answer for the measure. If I used a protractor and measured each interior angle of an 11-sided figure, that's what it would be. Similarly, you can find the measure of one interior angle of a regular polygon using the formula. Well, I guess we're just copying it over again. For the exterior, though, for just each side, each exterior, not side, I'm sorry, each exterior angle is going to be, well, we know the total sum was 360, and again you would divide that by the number of sides that you have. So each one of these, if you were again using an 11-sided figure, then you would have 360 divided by 11. That's going to give you another repeating decimal, 32.72 repeating degrees. So that would be your answer to the outside exterior angles. Okay, so you can do a whole bunch of these. You've got to know, go back to the notes, I think in section 5-1, that actually gave us what each one of these were. A nonagon is a 9-sided figure. The sum of the interior angles, you're going to use this formula, 9 minus the 2. That's going to give you 180 times 7, so the sum would be 1260. I think we've had that one before. And the measure of each interior angles is going to be taking that 1260 and dividing it by not 7 but 9, which would give you 140 degrees. Alright, similarly, the exterior angles, we're not looking at interior, we always know every single time, no matter what size regular polygon it is, it's always going to be 360. But again, this time you would take the 360 and divide it by 9. You would get 40 degrees. Don't forget your degree marks when naming degrees of angles. Okay, the last one on this page. Given a regular octagon, octagon would be an 8-sided figure, the sum of the interior is going to be 180 times 8 minus 2, so 180 times 6 is 1080. If you needed the measure of each interior angle, you're taking this sum measurement gotten by the formula 180 times n minus 2, and you would have had your 1080, and you're not dividing it by 6 but 8, the number of sides of an octagon, so that would be 135. Pause if you need to finish filling in any of these values. Okay, the last page is some of the exterior angles. We're still looking at a 9-sided figure. Sorry, 8-sided. This still goes with the example 7, which was an octagon. Again, write it big, 360. Always, always, no matter how big the polygon is, the sum of exterior angles would be 360. The interior angles, the exterior angles being each of them, you're going to take always 360 and divide it by the number of sides. This happens to be, not an angle measurement, 8 sides, so 360 divided by 8 is 45 degrees. Alright, 3 more examples. The exterior angles of a regular polygon is 30. Find the number of sides. This is where you actually know first the measure. So you're going to have 30 is equal to the 360, because we're looking for exterior, divided by n. That was our formula, and we're trying to find the number of sides. It has a denominator, so we're trying to get rid of that denominator. Multiply by whatever the denominator is on both sides of the equation. The denominator goes away, so now you have 30n is equal to 360. So you're dividing 360 by 30 to find the number of sides. Divide this by 30 on both sides, and you're going to get a 12-sided figure. So that's going to have 12 sides. Alright, we're going back and forth on these, and I think the worksheets do this too. You've got to remember the difference in the formulas of interior angles and exterior angles. So if you have a regular polygon that has an interior angle that measures 144, find the number of sides it has. We remember the formula for interior times n minus 2, all divided by n. We had an example like this before. You're having to multiply by n on both sides. These n's go away. 144n is equal to 180 minus 360. I'm running out of room. 180n minus 360. It's better to write them flat, straight across, if you've got room to do that. And remember, again, you're subtracting on both sides, and you're going to have a negative 36n is equal to, remember this was minus 360, so a negative 360. And of course, 2 negatives cancel out, and that's going to be equal to 10. So the number of sides is 10. Okay, again, this is a little bit of a review from previous ones dealing with the formula that the exterior angle, remember we kept drawing it with color orange, this is equal to, this angle measurement is equal to the sum of the 2 remote interior angles. So if you've got the 2 remote interior angles as being the values of 3x and 2x is 5x plus 9, and it's supposed to equal the x plus 21. If you work through and solve this, you're going to get x equals to 3. I'll give you a chance to either do this algebraically or try the trick we learned earlier, putting this into y1 and this into y2, and looking in your window in your calculator to see where they cross. This is just a trick of intersection. Second calc intersection, you'll be able to find the value of your single variable. But come see your teacher if you need more examples for that. And that concludes 5-4.